By the end of this video, you should be able to assign oxidation numbers to atoms and ions in a substance. Oxidation numbers are a way of keeping track of what's going on with the electrons throughout a chemical reaction. If I have an ionic compound, the charge of the ion is equal to its oxidation number. However, if we have a covalent compound, oxidation numbers are figured out by pretending that all of the electrons in a covalent bond have been transferred to the element that has the highest electronegativity. They're actually being shared, but we're pretending they've completely gone to the element with the higher electronegativity. The rules you're about to learn are going to give us a little bit of a shortcut of figuring out what the oxidation numbers are without having to draw a dot diagram for the compounds and look up the electronegativities. There are 6 rules that we're going to be learning for assigning oxidation numbers. The first one is a pure element has an oxidation number of 0. I'm using the abbreviation ON for oxidation number. So a pure element, which includes the atoms that are part of a diatomic element, or another element that comes as more than 2 bonded together. It doesn't matter how many atoms of that element I have. If I only have one element, the atoms are going to have an oxidation number of 0. So Cl, written by itself, a single atom of chlorine, is going to have an oxidation number of 0. Cl2, 2 chlorines bonded together, that's still a pure element, not a compound, even though it's diatomic. That is still going to have an oxidation number of 0, because I have the 2 chlorine atoms bonded together. Remember, the oxidation number takes and assigns those bonding electrons to the element that has the higher electronegativity. Well, chlorine and chlorine are going to have equal electronegativities, so we kind of evenly split those electrons, and we end up with an oxidation number of 0 on each of those. So a pure element, whether it's a single atom of that element or there's multiple of them bonded together, if it is a single element, it has an oxidation number of 0. This is one of the most commonly forgotten rules. Always check this one first. The others are all dealing with if I have elements that are part of a compound. Rule number 2 says a monoatomic ion has an oxidation number identical to its charge. So for example, Cl with a minus sign, that minus sign is telling me that I'm not dealing with an atom of chlorine, I'm dealing with an ion of chlorine. And an ion has an oxidation number of its charge. So this is a Cl minus ion, therefore it has an oxidation number of -1. So just to recap, Cl by itself, with no charge written, has an oxidation number of 0. Cl2, there's more than one of them, but it's still just chlorine, has an oxidation number of 0. Cl with a minus sign, that minus sign is telling me that I have the negative ion, so it has an oxidation number of -1. Rule 3 says metals from group 1. Notice it says metals from group 1, so we are ignoring hydrogen for right now, just looking at the metals from group 1, have an oxidation number of +1, since they're going to form ions with a +1 charge, since they have that 1 valence electron that they're going to lose. Again, this is when that element is part of a compound. If I have an element, even from group 1, sodium is a metal from group 1, but if I just have an atom of sodium, it's still 0. But if that sodium is part of a compound, it is going to have an oxidation number of +1. Elements from group 2 are going to have an oxidation number of +2 when they're part of a compound, because they always form ions with a +2 charge. Hydrogen has an oxidation number of +1, usually. So again, hydrogen is in group 1, so it kind of follows that metals from group 1 rule. It's usually going to be +1. However, if hydrogen is combined with a metal, metals always lose electrons, so metals are always going to have positive oxidation numbers. Hydrogen's a nonmetal. Hydrogen can lose an electron and form a positive 1 charge, or it can gain an electron and form a negative 1 charge. If hydrogen is with a metal, it's going to have to take the electrons from the metal, therefore the hydrogen would be forced to be a negative 1. So hydrogen almost always is going to be positive 1. However, if it's with a metal, the metal absolutely has to be positive, which means the hydrogen would have to be negative 1. Oxygen is going to have an oxidation number of negative 2. Again, almost always. The only time that one will not be the case is if other rules force the oxygen to be a negative 1 charge. And essentially that's going to be when we actually have a polyatomic ion of oxygen, O2, negative 2, the peroxide polyatomic ion. Looking at something, you're probably not going to notice right away whether it's a peroxide ion or there's just 2 oxygens in it. Assume that oxygen is negative 2. And then if something goes terribly wrong and you end up with charges that you can't have, try the negative 1. So, for example, H2O2, hydrogen is usually going to be positive 1, unless it's with a metal. Oxygen's not a metal, so it has to be positive 1 there. O2, we have 2 oxygens. Our next rule is going to be that the oxidation numbers for all of the elements have to add up to 0. Well, if I have 2 positive 1s and 2 negative 2s, that's not going to add up to 0, so I know something's wrong. But if I use the negative 1 for oxygen, then it ends up working out. So again, assume the oxygen is going to be negative 2, but double check and make sure that it works. If it doesn't, then go back and try and see if the negative 1 might end up making it work. Otherwise, you did something wrong somewhere else. All right. The last rule is how you're going to figure out all of the other elements. And it is the sum of oxidation numbers of all of the atoms in a compound is 0, because compounds overall are neutral. The sum of all of the oxidation numbers of all of the atoms in a polyatomic ion is the charge of the ion. One thing to keep in mind is the charge that's written on the polyatomic ion is for the entire ion, not the last atom. So for example, NO3 negative 1 tells me that the nitrogen and 3 oxygens as a whole have a negative 1 charge. It's not giving me a helpful hint of oxygen being negative 1. Alright. When you're doing this, you do need to take into account how many of each atom is present in the compound. Go through the rules first, and then you can use this rule to either verify that you did it correctly, or a lot of times there's going to be some element that we don't have a rule for, and we can use this to figure out what that other thing has to be. For example, with K2Cr2O7, if I go through my rules, potassium, K, is in group 1. So we know that group 1 metals have an oxidation number of positive 1. Therefore, the potassium has to be positive 1. Oxygen is, again, usually going to be negative 2. So we're going to assume it's negative 2, and unless things go terribly wrong, we're going to get an answer that works here. If things go terribly wrong, we could retry it with a negative 1. Chromium, however, does not have a rule. We do not know what the oxidation number is for chromium, so we're going to have to figure it out. The oxidation numbers of all of the atoms in a compound is 0. So if I add up 2 potassiums and 2 chromiums and 7 oxygens, they have to add up to 0. So 2 times potassium plus 2 times X for chromium, we're trying to figure out what that is, plus 7 times oxygen's oxidation number, have to add up to 0. I can go through and mathematically solve. 2 times 1 is 2, plus 2x, plus 7 times negative 2 gives me negative 14. Combining like terms, isolating x, I get that x is positive 6. So that tells me that chromium has to have a plus 6 charge, a positive 6 oxidation number. Now notice, 1 plus 6 minus 2 does not add up to 0. We're not just adding up the oxidation numbers for all of the elements, but for all of the atoms, taking into account how many of them there are in the compound. Same idea applies to polyatomic ions, but instead of having to add up to 0, it has to add up to the charge of the ion. So NO3 with a negative 1 charge. That means that the nitrate polyatomic ion has a negative 1 charge. We know the rule for oxygen is oxygen has to be a negative 2 charge. So oxygen has to be the negative 2 charge, again, unless things go terribly wrong. But we don't have a rule for nitrogen, so that's going to be our X. We have 1 nitrogen and 3 oxygens. So 1 nitrogen plus 3 oxygens has to add up to the charge on the ion, which is negative 1. So doing some basic algebra, we end up with, therefore, x equals 5. So now I know that the charge on the nitrogen, the oxidation number on the nitrogen has to be positive 5. When you're solving for the oxidation numbers of elements that we don't have rules for, when you're done, double check your reference table. On the periodic table, it does state selected oxidation states, and usually the oxidation numbers we're going to be using are ones that are actually on your reference table. It is possible to end up with some that are not. For example, oxygen, they only list the negative 2 charge. They don't list that negative 1 that occasionally pops up. But if you end up with something that's not listed as a selected oxidation number on your reference table, you probably did something wrong. Again, unless it's that exception for oxygen. So remember, if it is a pure element, it's 0. If it's an ion, it's the charge of the ion. Anything in group, or any metal in group 1 has to be positive 1. Any element in group 2 has to be positive 2. Again, if they're part of a compound. The hydrogen is almost always going to be positive 1. The only time it won't is if the hydrogen is combined with only a metal. Then the metal has to be positive, forcing the hydrogen to be negative. And then oxygen is almost always going to be negative 2, unless mathematically weird stuff happens. Then check and see if negative 1 will work. There are some other elements on your periodic table that only have one selected oxidation state. If you're using one of those, you can look that up. For example, zinc only has a positive 2 listed. So if zinc is in the compound, you know it's going to have an oxidation number of positive 2 as well. Everything else you're going to solve for mathematically using rule number 7. The sum of the oxidation numbers of all of the atoms of a compound is 0, and the sum of all of the oxidation numbers of all of the atoms in a polyatomic ion is the charge on